Hello friends, I welcome you in lecture number 37 on higher order ODEs. In this lecture, we are going to solve this differential equation, and this question was asked in GTU Winter 2022 exam. Now here we are given the differential equation x square d square minus 7xd plus 12y equal to x square, and we know that this d stands for derivative with respect to x. Therefore, d square is second order derivative with respect to x. So we can rewrite this differential equation as given ordinary differential equation is x square times d square y, that is second order derivative, minus 7x dy, that is y dash, plus 12y equal to x square, and we give this number 1. Now if you observe that here power of x is 2 and x square is multiplied with second order derivative. Similarly, power of x is 1 here and it is multiplied with first order derivative. Here there is no x, that means power of x is 0, and we have y multiplied with that x raised to 0, that is 0 derivative. This means every term in this differential equation is in this form, x raised to n into nth order derivative of y. And we know that if every term of differential equation is in this form, then it is called Euler-Cauchy equation. And if we have Euler-Cauchy equation, we can always convert it into differential equation with constant coefficients. So let me write that given equation is Euler-Cauchy equation, and if we have Euler-Cauchy equation, we will change the independent variable x to the new independent variable, say z, by some transformation, and we are using this transformation to change the independent variable x. We are using the transformation x equal to e raised to z, and if we have x equal to e raised to z, and if we take logarithm on both sides, we have log x equal to log of e raised to z, that is z, and this x into y dash, that is x into dy by dx, will be equal to dy by dz, and if we use d by dz equal to d1, then this I can rewrite as d1y, where this d1 stands for derivative with respect to z, and therefore second order derivative multiplied with x square will be equal to d1 times d1 minus 1y, where d1 stands for derivative with respect to z. In general, if we consider this transformation in Euler-Cauchy equation, then remember that this type of terms x raised to n into nth order derivative will be replaced by d1 into d1 minus 1 into d1 minus 2 and so on, d1 minus n minus 1 of y. If we have nth power, we will go up to n minus 1 subtracting from d1. If I have second power, that is x square into y double dash, then n is 2, so this is going to be d1 minus 2 minus 1, that is d1 minus 1. So for x square into y double dash, I will write d1 times d1 minus 1 y, where d1 is the derivative with respect to new independent variable, which is z in our case. So we will replace this x y dash by d1y, x square y double dash by d1 times d1 minus 1y in this number 1. So using all these things, we can see that equation number 1 reduces to, therefore 1 reduces to, first term is x square into y double dash, that we will replace by d1 times d1 minus 1 y, that is for x square into y double dash, minus 7 times xy dash. Xy dash is replaced by d1y, that is we have minus 7 d1y, and plus 12y equal to x square, plus 12y equal to x square. X is taken as e raised to z, so we have square of e raised to z. Now I can simplify this. I can take y common, and I multiply this d1 minus 1 with d1, and I will have d1 square minus d1. Here I have minus 7 d1 plus 12 y common, so this quantity in the bracket, and e raised to z whole square can be written as e raised to 2z. This I can again simplify. d1 square minus d1 minus 7 d1, that is minus 8 d1 plus 12 y equal to e raised to 2z, and we can see this is equation number 2 is linear differential equation with constant coefficients, which is linear ordinary differential equation with constant coefficients in new independent variable z. Dependent variable is y, but independent variable is z. So in y and z, original equation was in terms of x and y, and it is not differential equation with constant coefficients. You can see here coefficient of y double dash is x square. Here also coefficient is function of x, which is 7x. So this equation is not differential equation with constant coefficients, and we know that it is Euler-Cauchy equation. Therefore we can always convert Euler-Cauchy equation into differential equation with constant coefficients using this transformation x equal to e raised to z. Now once we have converted our equation into equation with constant coefficients, we know how to solve this. So first step is we will write down the homogeneous differential equation corresponding to this equation number 2. The corresponding homogeneous ordinary differential equation is, we will consider right hand side equal to 0, d1 square minus 8 d1 plus 12 y equal to, and we have to solve this first. So to solve this homogeneous equation, first we have to write down the auxiliary equation, that we write by replacing this d1 by lambda in this function of d1. Auxiliary equation will be lambda square minus 8 lambda plus 12 equal to 0. And let's try to find out solution of this auxiliary equation. And you can see, because I have 12 here, which is 6 into 2, I can rewrite minus 8 lambda as minus 6 lambda minus 2 lambda plus 12 equal to 0. And here I can take lambda common, I will have lambda minus 6. Here I can take minus 2 common, I will have lambda minus 6 inside the bracket. Again I will have lambda minus 6 common, and therefore I have lambda minus 6 times lambda minus 2 equal to 0, and this will give me two real and distinct roots. And here our equation is differential equation with constant coefficients in variables y and z, that is z is our independent variable. So therefore the complementary function will be equal to c1 times e raised to lambda z. Lambda is 2 and 6, so c1 e raised to 2z plus c2 e raised to 6z. This is the complementary function, and that we have obtained by solving this homogeneous differential equation corresponding to this non-homogeneous equation. Now next step is to decide the particular solution or particular integral, and here our right hand side function is exponential function. Therefore, we can find out the particular solution or particular integral using shortcut method. The particular integral is pi equal to apply shortcut methods. We can see here from this equation we can write y equal to 1 over d1 square minus 8 d1 plus 12 applied to e raised to 2z. So that I am writing here 1 divided by function of d1, which is d1 square minus 8 d1 plus 12 applied to e raised to 2z. And we know that if we have exponential function in shortcut method, then we concentrate on the coefficient of z, which is 2 here, and we replace d1 by 2 in this function of d1. Suppose I replace d1 by 2, then I will have 2 square minus 8 into 2 plus 12, which is 4 minus 16 plus 12, and this is going to be 0. If I take d1 equal to 2, this quantity becomes 0. So for that I have to take derivative of this function of d1 with respect to d1, and I have to multiply by independent variable, which is z here, and here I have to write derivative of this function. Derivative of d1 square is 2d1 minus derivative of d1 is 8. Derivative of 8d1 is 8 and derivative of 12 is 0. And then I have to again put d1 equal to 2. So if I take d1 equal to 2 in this 2d1 minus 8, I will get again 0. You can see that no, I will not get 0. This is going to be 4 minus 8, which is minus 4, and it is non-zero. So this will work. So now in the next step I will put d1 equal to 2 here. This is equal to 1 over 2 times 2 minus 8 e raised to 2z. We have taken d1 equal to 2, and this is 4 minus 8, that is minus 4, and we can see we have minus 1 by 4 z times e raised to 2z as the particular integral. So if you are familiar with shortcut methods, you can easily obtain particular integral. Here we can see that right hand side is e raised to 2z, therefore we can apply that method, shortcut method, and first we take d1 equal to 2 in this function of d1, but this becomes 0 for d1 equal to 2, therefore I multiply by z and I take derivative of this function, which is 2d1 minus 8. Then again I put d1 equal to 2 here, and I find that I am having 4 minus 8, that is minus 4, which is non-zero. Therefore this is my particular solution or particular integral. And once we have both the complementary function and particular integral, we can write general solution by taking their addition. General solution is y equal to complementary function plus particular integral. Therefore y equal to, let me check what is complementary function, e raised to 2z and e raised to 6z. c1 times e raised to 2z plus c2 times e raised to 6z. Particular integral is minus 1 by 4 z e raised to 2z minus 1 by 4 z e raised to 2z. Now this is the solution in terms of y and z, and we require solution in terms of y and x. And recall that we have taken x equal to e raised to z, that is e raised to z will be replaced by x, and if I have e raised to 2z, that I can write as square of e raised to z. E raised to z is x, that is I will have x square. Similarly e raised to 6z, will be equal to e raised to z raised to 6, that is x raised to 6 minus 1 by 4, and if I have x equal to e raised to z, z is log of x. So here I will write log of x into e raised to 2z, which is x square. And let me rewrite again, y equal to c1 x square plus c2 x raised to 6, and I am taking this x square before log x, so this is x square times log x, and this is the general solution of given Euler-Cauchy equation, where c1 and c2 are arbitrary constants. c1 and c2 are arbitrary constants. So this is nice question. We are able to apply shortcut method to obtain particular solution or particular integral, and because given equation is Euler-Cauchy equation, we are able to convert it into differential equation with constant coefficients, and then we can easily solve it. And so I stop here. I hope you like this session. Thanks for watching.